All right, we're going to pick up with this Boltzmann distribution graph right here. Monatomic being one atom of gas, so maybe all the gas particles in this case are helium, or maybe they're all argon, just one element making up the gases. And then Kelvin temperature is going to tell us the average energy content, usually kinetic energy. So a lot of students will see this and they'll say, hey, at 300 kelvins, the gas is moving faster, right? Because it looks like the taller graph. And then they'll see here and they'll say, well, this peak's lower. At 600 kelvins, they're not moving as fast. Well, make sure you're paying attention to the axes and these temperatures. Does that make sense? Does it make sense for helium to move faster at a lower temperature? It doesn't. So let's look and see what this graph is really showing us. The majority of the molecules have a velocity close to like 1,000 meters per second at 300 kelvins, right? So our average velocity right here is roughly, it looks like 1,000-ish. That's good enough. But at 600 kelvins, we could say, what's that look like? 1,500. Our average velocity equals 1,500 meters per second. So more particles are moving at a higher velocity at 600 kelvins. So the smaller peak actually has more particles with a higher velocity. So then here's another one. This time we're at the same temperature, all right? So notice the only difference between these two peaks is this one's oxygen and this one's helium. So why does helium have more particles moving at a faster velocity, close to 1,000, compared to oxygen that has particles moving roughly like 500 meters per second? So the big difference here is their molar mass. So you can see right here, this postulate letter D, heavier gases have lower average speeds at the same temperature. So if you think about it, this has a molar mass of 32 grams per mole. This one is 4 grams per mole. So we would expect this one to be able to move faster, and that's what this graph is showing us. All right. The last thing I want to point out before we look at the gas laws from Chemistry 1 are units of pressure. So we can have atmospheres, millimeters of mercury, pascals, barometric pressure. We can have kilopascals, we can have torr. We have all kinds of units for pressure. Most of the gas laws, it won't matter what pressure you have as long as it's the same on both sides. So you can see here, pressure 1, pressure 2. As long as they're the same, not a big deal. However, once we get to the ideal gas law and a few other formulas, we will want to convert to atmosphere because our R constant will have that value. So most of the time, I like to just get my gases to atmosphere. Just keep that in mind. Make sure you're writing your units when you're plugging in formulas and crossing out what can be, and that'll kind of give you an idea whether it needs to be in atmospheres or if you're good leaving in any of these other units. So here's just a few conversion factors in case you need to get from one unit to another. I believe these are given on exam, so don't worry about memorizing these. I know they are, so don't worry about it.